Go ahead, Kumar.
Um, hey everyone, so my name is Kumar Manivel and I am a graduate student majoring in computer science at the State University of New York, Binghamton. Uh, Joining with me is my teammate Gaurav. Um, so we had to do a project for our CS 575 class, design analysis and algorithm. So for that, in order to do that, what the project idea that we decided to do was plagiarism detection using string search algorithm. So what string search algorithm is? So according to Wikipedia, string matching algorithms are used, to identify a substring, which if the substring is part of a normal string. So this is used in like pattern matching and uh, more likely in DNA matching and then plagiarism detections and stuff. So one second. Yeah. So the in order to do this plagiarism detection, we decided to use three specific string matching algorithms. So the three string matching algorithms were the Knuth-Morris-Pratt algorithm, the Boyer-Moore algorithm, and the Rabin Karp algorithm. So from here on, Gaurav will be taking up on the Knuth-Morris-Pratt and the Rabin Karp, and I'll be talking about the Boyer-Moore algorithm. Go ahead, Gaurav.
Thank you, Kumar. So, before we start discussing about the algorithm, I would like to talk a few things about how, what plagiarism is and how we actually want to like approach this problem. See, we cannot actually just compare string by string and say that, okay, he has plagiarized from this source. And that probably won't work in this approach because let's say if he's changed one particular word, the entire sentence won't match and then the computer might reject it. So we have to develop a foolproof method to somehow prevent this from happening. So we actually do multiple steps in this. So primarily there are three steps. So we'll just go by one what these are. So this was the primary paper that we actually took when we were, when we wanted to initially start developing the algorithm. So there were primarily four steps he talks about. So for the last step will vary for algorithm by algorithm, which is the hashing, but the first three steps are common. First is tokenizing, the second is stop word removal, third is stemming, and this for this particular algorithm, which is Rabin Karp, will be hashing, but it'll vary for different algorithms that we've tried to use here. So what are these? So basically tokenizing is just taking those words and we just split everything. Like we break it down into an array where each word is a item in it. And then we go for stop word removal. Stop words are primarily common words like is and like prepositions, some of the pronouns and conjunctions, and all these will be removed. That also improves the performance of the algorithm because we just need to see the main words. And then stemming is really interesting. What stemming is actually is when you have certain words like arriving has multiple forms like arriving, arrived, arrive. So what the algorithm does is it has to detect what all different forms are there, and it has to cut the last few letters of the word starting from the end, so that it will become a unique word. For example, arrived becomes arrive, because everything after arrive will always be changing. So we'll just go over the code once. So this is the KMP approach that we had taken, but Basically, this def stem sentence is basically for stemming the word which we've just discussed about, and that is from the NLT key package of Python. And here I'm just removing the slash ends and a couple of punctuation marks and all that over here. And then here is where this function basically just removes all the common words that you see. And I've just made a list of some of the common words we are removing, but this can be like added and changed how much ever we need. So that's the main like the main introduction that I wanted to do. Now let's go back and let's discuss a little about uh, uh, KMP algorithm. Okay, so what is KMP algorithm? It's a searching algorithm that searches the occurrences of a word within a text string. This is it. It's not like, I mean, that's what all searching algorithms are, but basically what is the advantage of this is it improves the worst case complexity to O of n, whereas the complexity for naive Bayes is so the naive string matching is mn, which is the pattern, and the m will be the length of the pattern and n will be the length of the particular string. So there are two particular things in KMP. First is the prefix function, and second is the KMP matcher, which actually starts matching with the, which is actually the main part of KMP. This is just the pre-processing that we do. So you can see there's a pseudocode here, but I'll just explain the overview of what exactly happens in the pi table. So pi function, basically what happens is it'll look at repeating patterns. Like for example, if you have A, B, A, what will happen is it'll generate a sequence where it'll tell you like where all the patterns are being repeated. For example, A will be 0, 0, and then B would be a 0. But as soon as it detects one A, again it's going to write 1, 1, telling that I have already detected this particular character in the beginning of the pattern. And so what happens now? Let's say you have a string of let's say if you have any string that is A, B, C, D, and then let's say you're starting to match it with your pattern. In case a mismatch is detected after a particular letter, let's say now if you have the pattern of A, B, A, and then now the mismatch has occurred at the first A after B. So now instead of comparing the whole thing again, it'll automatically jump 3 characters ahead, because it knows that the before 3 characters have not been matched, and then it'll start again from matching from A. So that's Knuth-Morris-Pratt, and that's the basic overview of it. Kumar will tell you a little bit more about Boyer-Moore's algorithm.
Thank you, Gaurav. So that was really impressive and comprehensive. Gaurav would have he explained about tokenizing and stemming and all the processes. Gaurav, could you pull out the code for Boyer-Moore algorithm, please?
Sure. This is the code for Boyer-Moore.
Yeah. So thank you, Gaurav. So if you notice in the code, the first 3 steps in this in the code is pretty much same as Knuth-Morris. We are just reading the file and then stemming the file and then tokenizing the file. But what actually different? What actually sets this different from the previous one is the last function that we're defining over here. So how exactly Boyer-Moore works is, as I had mentioned earlier, the main goal in a string matching algorithm is to find a substring, to identify whether a substring is part of a string or not. So let's assume there is a substring. Let's assume we want to identify whether a substring ABCD is part of a string, let's say EOVAD ABCDF, something like that. So the first step in Boyer-Moore would be is to construct a bad match table. So to construct this bad match table, we would need to assign, we would have to assign a specific value to the each alphabet or character in the string. So how do we calculate this value? So the formula for this value is the length of substring minus index of each letter in the substring minus 1. So the value of the last letter and other letters that are not in the substring will actually be the length of the substring. So after once we calculate this value will be assigned to every letter in a bad match table. So what happens after we have found out a bad match table? So after this, we'll have to compare the substring with the string. So when we do this, since it's a Boyer-Moore algorithm, we have to start the comparison from the index of the last letter in the substring. So let's assume so once we start comparing, if the letter matches with the letter, and if the substring letter that we are considering as an example matches with the letter in the string, we should compare the previous letter of which we have taken from the substring. In case the letter does not match, we should check the value in the bad match table of the letter in the string that we wanted to compare, and move the number of spaces according to the value that we had. So we have to continuously keep on repeating these steps until all the letter matches. So that is what we have performed in this. And let me go back to the PPT. So yeah, so this was part of our code. uh, and then the complexity in the worst case for the Boyer-Moore would be O of mn, where m would be the length of the pattern and n would be the length, and the average time taken for computing would be O of n. Ideally, this Boyer-Moore algorithm is used in a lot of applications such as autocorrectors, big data, and search bars. So I think that's all for Boyer-Moore, and Rabin Karp would again be explained by Gaurav.
Yeah, thank you, Kumar. Yeah, that was a good explanation. So now let's come back to Rabin Karp, and the primary goal of the whole most of the concept of Rabin Karp revolves around the concept of hashing. So what we do here is we have something called rolling hash, and we have a hash. We have first we take a pattern that we have and we generate a hash, and then we keep comparing that hash with each. Then what we do is we take the number of characters in the document or in the main text pattern that we want to search in, and it is converted into a hash continuously, and it is compared with the with the hash of the pattern that we have. So yeah, here you can see how it works basically. It's pretty comprehensive, like and sometimes the hash sometimes can be any function that we use here. And here I can just go back to the code and just show you what hash pattern that we have taken. So you can see here that we have we are converting the string into an ASCII character. We are seeing this D here is basically specifying the length. So D here means like I have set the character saying that in a string you can have at the most 256 characters. That's why I've used D here. And then we are dividing it by Q. Q is any prime number here. We have to choose a mid-sized prime number so that like because it will be like because they'll avoid collisions within the hash pattern. So we basically just keep comparing like that. Oops, sorry. Yeah, so you can see the pseudocode here. You just calculate the hash and keep moving the hash forward in the string and keep calculating the rolling hash, and we compare it, and if it does match, then then it works, and if it's a match, and if it doesn't match, then you can understand that there have been no similarities in the pattern and the text that we've provided. Yeah, so you can just see a little bit of the output here from the test scripts we have taken. So basically, it will show the number of matches that are there, and it will show the rate of plagiarism. And how we calculate the rate of plagiarism is basically, again, we can just go back to the code once, and I can show you. Basically, rate of plagiarism is just 2 into the number of matches that we found, divided by number of sentences in the document 1, and plus number of sentences in document 2. So that's how we calculate the rate of plagiarism. I'll just show you the we'll output once again from the PPT. And
Gaurav, sorry to interrupt. So I think it'll be better if we just we run the code maybe, if that's possible. That's good with you.
yeah, sure, we can just run the code once then.
Yeah, that'll be good.
Oops, I think I just opened the wrong one. This is the one needed. So So this was for the Rabin Karp that we had shown, and I'll just show you some of the so I can show you some of the things that we were talking about in the PPT. So I'll just increase the font size a little here. So you can see certain words here. He says you can see the word arrived has become ARRIV, and then certain words like themselves has been the last few letters have been dropped. Earlier, the last few words have been dropped, and following has become folly. So certain words are stemmed. So this is basically stemming, and you can see that this is the sentence from document 1, and this is the sentence from document 2, and they're getting compared. And if there are matches, it'll just store the matches, and then it's going to just compute the rate of plagiarism. And I think the last output for the other two will be a little I mean, it has lesser information because we've just shown you above how it works, but I'll just go through that once. So you can see that rate of play, it just runs the same Boyer-Moore's algorithm, and then it will just show you how much the rate of plagiarism is. And similarly for KMP2. So yeah, you can see that we have 42.8% of similarities in this, and we were using these test files. So some of the words that you have seen above, like the staying and all, and arrival has become arrive. So you can see some of the letters, how they have been changed, and see, like for example, majority over here has become major in this particular sentence. So that's how it basically works. And we'll go back to the PPT. So that's the output. And here we have just explained the best case running for uh, each algorithm, and you can see that KMP has the best performance. Actually, Boyer-Moore seems to seems to have the best performance here. But then again, you can see that it depends on N and M, but KMP, it only depends on its O of N. So pretty much everything is linear when you consider best case scenario. But go to the worst case, actually, you will notice here that Boyer-Moore and Rabin Karp are almost the same, like they have the same worst case, so they might not perform better than KMP, which is O of N, which only depends on the which probably only depends on N could be here the length of the text, the length of the document, where it has to just in one pass it can determine how good if there are any matches or not. And thank you.
So yeah, that was our presentation on our CS 575 project. Hope it was comprehensive and it was good. Thank you, everyone. Thank you.